In 35 hours, a rare long-period comet's plasma tail is about to slam into Earth's orbital path, and the timing could not be worse. 3 other space weather systems are converging on the same 48-hour window: a flare-productive sunspot region, a high-speed coronal hole stream, and the ongoing aftershock sequence from Japan's magnitude 7.4 earthquake. Only one spacecraft in human history has measured something like this, and it was all the way back in 1996. Here's what scientists are actually looking out for, and why it matters. Let's get into it. A comet you have probably never heard of, discovered only months ago, is about to do something that has only been directly measured one time in human history. Its name is Comet C/2025 R3, nicknamed PANSTARRS, and in roughly 35 hours, Earth is projected to cross through its plasma tail. The date to mark is April 25th and 26th, 2026. That is this Saturday and Sunday. The plasma tail's sweep window opens at approximately 0000 hours Universal Time on Saturday morning and runs for roughly 48 hours. PANSTARRS was discovered by the Pan-STARRS Telescope Survey in Hawaii in late 2025. The designation prefix, the letter C followed by a slash, tells astronomers this is a long-period comet from the Oort cloud, making its first documented visit to the inner solar system. It passed through perihelion, its closest point to the Sun, 4 days ago on April 19th, at a distance of roughly half an astronomical unit. That is closer to the Sun than Mercury. Now, before anyone starts panicking, let me be absolutely clear. The comet itself never comes anywhere near Earth. The nucleus, the solid body, which is likely only a few kilometers across, stays tens of millions of kilometers away throughout the entire encounter. There is no risk of impact. There is no close flyby. What is crossing into Earth's orbital neighborhood is not the comet. It is the comet's plasma tail. And the only other time in history that spacecraft have directly measured a long-period comet's plasma tail at Earth orbit distances was in 1996, by accident. We will get to that story. But first, let me walk you through what a plasma tail actually is. Why Earth is about to fly through a comet's tail. A cometary plasma tail is different from the dust tail you see in photographs. The dust tail is physical debris, tiny silicate particles pushed away from the Sun by radiation pressure. That is the white or yellow streamer almost everyone pictures when they think of a comet. The plasma tail is a completely different structure. Also called the ion tail, it is invisible to the naked eye in most cases, and runs in a different direction from the dust tail. When a comet gets close to the Sun, intense solar ultraviolet radiation strips electrons off the gas molecules boiling off the nucleus. Water, carbon monoxide, hydroxyl compounds, the typical cometary inventory, get ionized almost as soon as they leave the surface. The solar wind then takes over. Its embedded magnetic field lines drape around the comet like fabric over a post, dragging the ionized plasma directly downstream. This is called magnetic field draping, and it produces a tail that always points directly anti-sunward, regardless of which direction the comet is physically traveling. That plasma tail can stretch 1 to several astronomical units downstream, hundreds of millions of kilometers. It is extremely low density, but it is magnetically structured, meaning it carries a detectable fingerprint of the comet, even far from the nucleus itself. According to current orbital elements from the Minor Planet Center, Earth's orbital path intersects the projected anti-sunward volume of the PANSTARRS plasma tail during April 25th and 26th. The Sun, Comet, and Earth are in near alignment, with the Comet inside Mercury's orbit, and Earth 1 astronomical unit out. The comet's tail, which always points directly away from the Sun, is briefly pointed at a slice of space that Earth will pass through. The timing margin is narrow, a specific 48-hour span. If the orbital elements are off, the geometry misses Earth entirely. What does passing through actually mean physically? Not much that any person on the surface of Earth would notice. The plasma density is extremely low, comparable to or below the ambient solar wind. You will not feel anything. No power grid is at risk from this event alone. No aircraft will be grounded. What could change measurably are 3 things. First, the direction and strength of the interplanetary magnetic field as detected by spacecraft at the Sun-Earth first Lagrange point. Second, the composition of the solar wind itself, if the water group ions from the comet are detectable above background. And third, potentially a minor enhancement in geomagnetic activity. 4 spacecraft are in position to observe this event. A CE and DSCOVR both sit at the L1 Lagrange point, monitoring solar wind continuously with magnetometers and plasma instruments. Stereo A, which orbits the Sun ahead of Earth, carries a heliospheric imager called HI2 that can photograph cometary plasma structures against the background stars. And ground magnetometers globally will register any geomagnetic response at Earth's surface. 2 independent vantage points, one from L1, one from stereo A, is something observers did not have the last time this happened. Here is what happened the last time a spacecraft directly measured a long-period comet's plasma tail. Comet Hyakutake, full designation C/1996, B2, was one of the brightest comets of the 20th century. It was discovered on January 30th, 1996, by a Japanese amateur astronomer named Yuji Hyakutake. Within days, professional observatories confirmed it was a long-period comet inbound on a near-parabolic orbit. It was one of the closest comet approaches to Earth in the 20th century. Hyakutake passed within about 15 million kilometers of Earth in late March of that year, close enough for its plasma tail to stretch across more than half the sky. As it turned out, Hyakutake was also the last time anyone had the chance to directly measure what we are about to measure, a long-period comet's plasma tail sampled at astronomical unit distances downstream. On May 1st, 1996, the Ulysses spacecraft, a joint NASA and European Space Agency solar mission, was doing routine solar wind sampling at high solar latitudes. Its magnetometer suddenly registered a sharp magnetic field reversal. The direction of the interplanetary magnetic field flipped within a span of minutes, too clean to be random solar wind variability. Nobody knew what had caused it at the time. After-the-fact trajectory analysis revealed the truth. Ulysses had passed through the ion tail of Hyakutake at a downtail distance of roughly 3.8 astronomical units. That is more than 500 million kilometers downstream from the comet itself. The analysis was published in the journal Nature in the year 2000 by Jones, Balog, McComas, and Grant. Volume 404, pages 574 through 576. The paper remains the canonical reference for cometary plasma tail behavior at large downtail distances. The Jones 2000 paper documented 3 things in the Ulysses data. First, a textbook magnetic sector boundary. The interplanetary magnetic field flipped cleanly across the crossing, consistent with the draped field structure around a cometary plasma source. Second, a characteristic ion composition signature distinct from ambient solar wind, including water group species that only come from cometary gas. Third, plasma structure preserved across astonishing distances. Before that paper, most researchers assumed cometary plasma tails diffused into background solar wind well before reaching 1 astronomical unit downstream. The Ulysses crossing showed the structure holds together far longer. It was a textbook rewrite result. The difference this time is that we know it is coming. ACE and DSCOVR at L1 continuously stream high cadence magnetometer and plasma data to Earth. Stereo A provides an independent vantage point that Ulysses did not have, and scientists have a chance to confirm the Jones 2000 observations at a different downtail distance, probably around 2 astronomical units instead of 4, with modern instrumentation. It would be the first such measurement made with advance notice, changing the data collection from accidental fly-through to deliberate target of opportunity. But what might prevent a clean measurement is everything else arriving in the same window. And this is where the story stops being just about a comet. At the same time the plasma tail is sweeping past, 3 other independent systems are converging on the same 48-hour window. This is the part that makes the current situation unusual, and this is the part that has driven most of the viral traffic this week. Driver 1 is on the Sun. A magnetically complex active region, designated Active Region 4420, has rotated onto the Earth-facing side of the solar disk. In technical terms, it is classified as a dromagnetic classification with beta-gamma polarity, which in plain language means its magnetic field is tangled enough to produce flares. Beta-gamma regions have opposite polarity sunspots in close proximity, which stores magnetic energy in twisted field structures that can release suddenly as solar flares. The Space Weather Prediction Center's 3-day forecast puts the probability of C-class flare activity at 75%, M-class at 10%, and X-class at 1% over the sweep window. For reference, C-class flares are routine and have minimal Earth impact. M-class flares can cause brief radio blackouts on the sunlit side of Earth. X-class flares at the top of the scale can cause more significant radio blackouts, and if they launch an Earth-directed coronal mass ejection, can trigger severe geomagnetic storms. Put another way, flare activity during the April 25th to 26th window is essentially certain. The only question is how strong. The sunspot region covers an area of roughly 180 millionths of the visible solar disk. That is moderate, big enough to be visible with proper solar filters, not a record-breaking monster. But its magnetic complexity is what matters here, not its raw area. Driver 2 is also on the Sun, but driven by completely different physics. A positive polarity coronal hole has rotated into a geo-effective position, and it is producing a high-speed solar wind stream forecast to arrive at Earth on April 24th. That is one day before the plasma tail window opens. Coronal holes are regions of the solar corona where magnetic field lines open out into interplanetary space, rather than looping back down to the sun's surface. Solar wind escapes through these open field regions at speeds much higher than the surrounding corona, typically 600 to 800 kilometers per second versus the usual 400. When Earth rotates into the stream, the faster wind arrives, compresses against the slower ambient solar wind ahead of it, and drives geomagnetic activity as the compressed region slams into Earth's magnetosphere. Coronal hole streams routinely elevate solar wind speed and drive geomagnetic activity, and this one will almost certainly produce high-latitude auroras independently of anything cometary. If you live in Canada, the northern tier of the United States, Scandinavia, northern Russia, or New Zealand, you may see auroras this weekend, but those auroras will be driven by the coronal hole stream, not by the comet. Driver 3 is on Earth. The magnitude 7.4 earthquake that struck off Japan's Sanriku coast on April 20th, we covered that event on this channel 2 days ago, is still producing aftershocks. 7 cataloged magnitude 4.5 or greater events have occurred in the 34-hour window ending this morning. The magnitudes in order are 4.8, 4.7, 5.4, 5.6, 5.3, 4.5, and 5.0. Depths range from about 10 kilometers to roughly 57 kilometers. Most are shallow subduction zone thrust events along the Japan Trench Plate interface, where the Pacific Plate is diving beneath the Okhotsk microplate at roughly 8 to 9 centimeters per year. The sequence is tracking within the normal Omori's Law aftershock decay envelope, elevated but not anomalous for a magnitude 7.4 main shock. Omori's Law, first formulated by Japanese seismologist Fusakichi Omori in the late 1800s, describes how aftershock rates decay following a main shock, roughly in inverse proportion to time since the main shock. The April 21st and 22nd rate is consistent with what that law predicts. USGS Pager, the Rapid Assessment System for Earthquake Impact, remains green, the lowest level, meaning no significant casualties or economic losses are forecast from the aftershock sequence. No revised tsunami advisories are in effect. The situation is stable, but the sequence is continuing. Let me be completely clear about one thing before going further. Earthquakes are not caused by comet tails. The physics does not exist. Japan's main shock occurred on April 20th, 5 days before the comet's plasma tail sweeps past Earth. The earthquake literally happened before the comet got anywhere near us. Cause does not flow backwards in time. Any claim that the comet triggered the earthquake fails on temporal grounds alone, before you even get to the physics. What makes the aftershock sequence relevant to today's story is that it is the fourth independent system producing data in the same convergence window. It is a scheduling coincidence, not a causal chain. That is the entire editorial framing here. And that is what makes this particular convergence scientifically unusual. Each event on its own is unremarkable. A long-period comet passing through perihelion happens most years. A magnetically complex sunspot region happens most months. A coronal hole high-speed stream happens most weeks. A major earthquake aftershock sequence happens multiple times per year somewhere on Earth. What is rare is having all four happen inside a narrow 48-hour window at the same time, because the joint probability of 4 independent events collapses quickly as you multiply them together. If you pick conservative base rates, a favorably aligned long-period comet is a once-per-decade event. A flare-productive sunspot region on the Earth-facing disk in any given week is maybe 1 in 3. A geo-effective coronal hole stream arrival in any given week is maybe 1 in 5. And an ongoing M7 plus aftershock sequence in progress at any given moment is maybe 1 in 20. You multiply those, and you get something on the order of 1 in several thousand. That is a loose calculation, not a formal statistical treatment, but it illustrates why the convergence is getting attention, even though no individual component is extraordinary. That is why headlines about this particular weekend are louder than the physics of any single event would justify. Compound rarity. 4 systems, all scheduled for the same 2 days, none of them causing each other. And that is exactly the situation where observational science gets interesting, because the universe is essentially running a natural experiment and handing scientists 4 simultaneous datasets to analyze. There is a theory circulating online right now claiming the comet's plasma tail will trigger earthquakes, take down electrical grids, or cause some kind of geomagnetic catastrophe. Some versions go further, claiming the convergence is evidence of some kind of orchestrated planetary event. Let me state what the data actually shows, and then we move on. First, plasma density. A cometary ion tail at 2 astronomical units downtail carries a plasma density orders of magnitude below ambient solar wind density. Typical solar wind densities at Earth are around 5 to 10 particles per cubic centimeter. A comet plasma tail at A/U scale downtail distances is dramatically thinner than that, often by factors of 10 to 100. The total kinetic and magnetic energy in the tail that reaches Earth's orbital volume is far below what would be required to couple meaningfully into Earth's magnetosphere, let alone into power infrastructure or the lithosphere. You cannot cause a blackout with a gust of wind that is thinner than the air already blowing through the room. Second precedent, the Ulysses Hyakutake crossing in 1996 produced instrument-level signatures, clean data on a magnetometer, distinct ion composition on a plasma sensor. That is what we saw. It did not produce any planetary scale effect anywhere. No grid impact, no earthquakes, no magnetic disturbance at Earth's surface that was traceable to the event. It was a beautiful measurement for space plasma physicists. It was not a disaster. There is no historical example of a comet tail causing Earth surface effects, because comet tails do not carry enough energy to do it. Third, scale. The strongest space weather events in recorded human history, the Carrington event of 1859, the Quebec blackout of March 1989, were driven by direct coronal mass ejection impacts carrying magnetic energies many orders of magnitude larger than anything a comet tail can deliver. The Carrington event produced auroras visible from the Caribbean, set telegraph lines on fire in North America and Europe, and delivered what modern estimates put at roughly 10 to the 25 joules of energy into Earth's magnetosphere. Pete Riley published an analysis in the journal Space Weather in 2012, estimating that Carrington-class events have roughly a 12% chance per decade. That is a real and significant risk, but it is driven by CME impacts, not by comet tails. Comet ion tails are not in the same energy category. They are not close. Fourth, earthquake energy budget. A magnitude 7.4 earthquake releases roughly 10 to the 15th joules of elastic strain energy. That is 1,000 million joules, released from rock that has been accumulating strain for decades or centuries of plate motion. No plasma interaction at Earth orbit distances has anything close to that energy available. Even the most extreme space weather events on record, several orders of magnitude stronger than anything a comet can produce, do not trigger earthquakes. The physics of seismic rupture is driven by tectonic stress accumulation and fault mechanics, not by atmospheric or magnetospheric events. Comet tails do not trigger earthquakes. The mechanism does not exist. The interesting part of the PANSTARRS encounter is the statistical coincidence of 4 independent systems converging on the same window. Not any mechanistic link between them. The science here is in the signal extraction, not in any causal chain. Keep that frame in mind as we look at what the spacecraft will actually be watching. Here's what scientists will actually be watching over the next 72 hours, starting right now. The first target signature is the interplanetary magnetic field at the Sun-Earth First Lagrange point. A CE and DSCOVR both carry magnetometers that sample the field direction and strength continuously, typically at once per second cadence. Analysts will be looking for a brief, clean magnetic field rotation or sector reversal consistent with the Jones 2000 Hyakutake profile. Specifically, they expect to see the field direction flip, not gradually, but within minutes, then hold that flipped orientation for some period of time before flipping back as the spacecraft exits the cometary plasma structure. The duration of the crossing depends on how thick the plasma tail is at that distance and how fast Earth is moving through it, but rough estimates put it somewhere in the range of hours to maybe a day at most. The second target is solar wind ion composition. When a comet tail passes through a spacecraft's location, water group species and other ions from cometary gas, hydroxyl, carbon monoxide ionization products, should appear in solar wind plasma sensors. These species are not normally present in ambient solar wind. ACE carries an instrument called SWICS, the Solar Wind Ion Composition Spectrometer, designed to identify minor ion species by their mass-to-charge ratio. SWICS data from the sweep window will be scoured for exactly this kind of cometary signature. The third target is a subtle geomagnetic response at Earth. Any low-level Kp index deviation above what the coronal hole stream alone would produce could indicate the plasma tail interacting with Earth's magnetosphere. This is the hardest of the three to interpret because it requires subtracting out the expected coronal hole response. The fourth piece of the puzzle is stereo A imaging. The HI2 instrument has captured plasma tail disconnections and kinks in past cometary observations. If the imagery from this week shows any unusual structure in the PANSTARRS tail, that can be correlated with spacecraft in situ data to build a three-dimensional picture of what happened. Here is the complication. The coronal hole stream arriving April 24th will drive its own geomagnetic response. That is the loud signal, high solar wind speeds, elevated magnetic field variance, sustained moderate activity for 2 to 4 days. Extracting a faint cometary contribution from that background noise is the hard part of this analysis. An effective region, 4,420, produces a moderate or large flare during the window. Solar energetic particle events will add even more noise. A significant X-class flare during the plasma tail window would be unfortunate timing. Best case, a clean magnetic field reversal shows up on A, C, E, and DSCOVR during the sweep, paired with a matching ion composition spike on SWICS with stereo A imagery showing correlated structure. That would make PANSTARRS the second confirmed cometary tail crossing in history and the first one observed with advance notice, a publishable result, a textbook update. Worst case, everything else arriving in the same window is loud enough that cometary signatures get buried in the noise. The data still gets analyzed, but the signal to noise is too poor to publish a clean result, and the community has to wait for the next long-period comet with favorable geometry, which could mean decades. Here is what to watch for over the next 48 hours with specific timing. Tomorrow, April 24th, the coronal hole high-speed stream arrives. Expect elevated solar wind speed, jumping from the current ambient 400 kilometers per second up towards 600 or 700, and high-latitude auroras. Anyone in Canada, the northern tier of the United States, Scandinavia, northern Russia, or New Zealand should check space weather forecasts. Conditions favor visible aurora if you have dark skies and clear weather. The best viewing window is likely the night of April 24th into the early morning of April 25th. Saturday, April 25th at 0000 hours Universal Time. That is 8 p.m. Eastern Time on Friday evening for U.S. viewers. The plasma tail sweep window opens. A CE and DSCOVR will be sampling magnetic field and plasma composition continuously. Any anomalous signal consistent with the Jones 2000 Hyakutake profile will be flagged in near real time. Expect preliminary chatter on space science social media within hours if anything interesting shows up. Saturday and Sunday, the sweep continues. Stereo A's HI2 imager has a favorable vantage point to photograph tail morphology from outside Earth's orbit. Any disconnection events or kinks visible in HI2 imagery will be correlated with in situ spacecraft data. Active region 4,420 stays on the Earth-facing disk throughout the window. Most flares will be C-class and have no Earth impact. An M-class flare would cause brief radio blackouts on the sunlit hemisphere. An X-class flare, if it happens, would be a bigger story on its own. The Japan aftershock sequence continues on its normal Omori decay. No tsunami advisories are in effect. No new main shock is forecast. If you are in Japan or on the Pacific coast, standard earthquake preparedness is the right response. Nothing related to the comet. Monday, April the 27th, preliminary analysis begins. Research teams at NASA Goddard, the University of Michigan, Imperial College London, the Max Planck Institute, and others will start working through the ACEDSCOVR and stereo A data looking for Hyakutake class signatures. Publishable results will take weeks to months. Do not expect definitive answers this weekend. Here is what to ignore. Any claim that the comet is going to trigger a grid failure, cause an earthquake, or produce some kind of electromagnetic catastrophe is not supported by the physics, not supported by the historical record, and not supported by any mainstream space weather assessment. Any aurora activity you see is overwhelmingly the coronal hole stream, not the comet. Here is what would actually be a big deal. If spacecraft data from the sweep window produces a publishable Hyakutake class signature, a clean magnetic field sector, reversal paired with cometary ion composition on SWICS, ideally correlated with stereo A imagery, that becomes only the second confirmed long-period comet plasma tail crossing in human history, and the first one observed with advance notice. That is the headline to watch for in the coming weeks. Here is the one-sentence takeaway. 4 independent systems are arriving at Earth's orbital neighborhood inside the same 48-hour window, driven by physics that have nothing to do with each other, and the universe is essentially running an experiment for us. Whether the spacecraft data contains a measurable Hyakutake-class signature from Comet PANSTARRS depends on how loud the rest of the stack is, and we will know more over the weeks following this weekend. We will be tracking this as it develops. This is the Space Desk.